expected. There were 9,307 on March 18th, somewhat further below our 10,000 expected. But by March 25th, the effects of social distancing became visible with 68,905 cases. On April 3rd, 250,000 cases, and on April 11th, 509,000, a factor of 200 less than our worst-case scenario. The drastic measures we took as a society saved millions of lives. Had we acted earlier, even more would have been saved. Had we waited longer, an even greater catastrophe would have unfolded. Indeed, states and localities that acted earlier generally did better. Around the world, similar stories played out. Subsequent months saw waxing and waning of the virus tied to behaviors, improved treatment strategies, and the eventual rollout of vaccines. But powers of 10 need not always tell such a grim story. They are a valuable tool for thinking about nature. We humans occupy a tiny planet in a vast universe. At the same time, there is a world of far tinier things, molecules, atoms, protons, neutrons, and electrons. Powers of 10 are also a useful concept in these happier pursuits. In 1977, while a graduate student visiting the Smithsonian Institution with my brother, I watched the video Powers of 10 by Charles and Ray Eames, a couple best known for their work in industrial design. This beautiful film summarized our understanding of nature at that time on the largest and smallest scales. Starting with a couple enjoying a beautiful spring day, occupying a space maybe 2 meters across in each direction, it explored scales progressively larger by factors of 10. Parks, cities, states, nations, the planet, the solar system, galaxies, and clusters of galaxies. It then proceeded in the other direction, describing smaller scales, parts of the human anatomy, then cells, atoms, and the nuclei of atoms. It summarized for me pretty well what I was learning in my studies. To be honest, there was a good deal I didn't yet know in that film. A lot has happened in the subsequent decades. We understand nature at scales several powers of 10 larger and several powers of 10 smaller, and we have clues to many more powers of 10 in each direction. I have been a witness to, and in some cases a participant in, many of these developments. Telling this story of nature on this vast range of scales is the subject of this book. The story follows this progress in physics, astrophysics, and cosmology. I will only occasionally mention the spectacular discoveries of the past century in biology, medicine, computer and cognitive science, and other fields. These advances have been the product of dedicated work of experimenters and theorists. The dichotomy between the two can be a confusing one, but one which will, I hope, become clear in these pages. While I seriously considered a career in experimental physics, as a student I fell in love with theoretical physics. This was, professionally, a risky choice, and some of my mentors discouraged me, telling me that the competition was just too stiff. While I believed them and was by no means convinced that I had the stuff for theory, I was in love with the subject. My graduate student days were spent studying phenomena at the smallest scales then accessible, about 1/3 the size of an atomic nucleus, or 10 to the minus 14th centimeters, 1/100th of a trillionth of a centimeter. I have to confess that I was hardly a brilliant student, but my teachers had faith in me and I went on to do a postdoctoral fellowship at the Stanford Linear Accelerator Center in Menlo Park, California. Here I was involved in interpreting experiments on still smaller length scales. Among my mentors were Sidney Drell, a leading voice for nuclear arms control, and Leonard Susskind, then a brash young theorist who had recently come to Stanford. Still, though, I had a hard time finding my way in that period. The problems I worked on didn't really move me. After 2 years at Stanford, I went on to a similar position at the Institute for Advanced Study in Princeton. The Institute is an institution exclusively devoted to theory, and it is famed, in part, because of the faculty of its early days. This includes, most notably, Albert Einstein, but also figures like J. Robert Oppenheimer, who headed the atomic bomb effort at Los Alamos during the Second World War, John von Neumann, an early computer pioneer, and George Kennan, the diplomat who shaped much of U.S. policy relative to the Soviet Union in the early days of the Cold War. Its current faculty, including Edward Witten, Nathan Seiberg, Juan Maldacena, and Nima Arkani Hamed, are among the premier